name is Alex, and this is Lab 3, Circuits. The purpose of this lab was to understand how simple circuits work, including how potential difference, resistance, and current are all related, and we did this by simulating several series and parallel circuits, and examining the effects that resistors and capacitors had on those circuits, and then we compared simulated values to calculated values, and the results were that in the 2 resistor circuit, the current was 0.02 amps, that the charge and discharge time increases with an increase in resistance. I calculated the time constant for a particular circuit to be 6 seconds, and the simulated values were very similar to the calculated values. So for some key concepts for this lab are the loop rule and the node rule. So the loop rule basically says that the round-trip potential difference across a battery is 0, independent of the path, the circuit components or materials, and this obeys conservation of energy. And the node rule states that the current entering a node must equal the current leaving that node, and that obeys conservation of charge. Resistance follows Ohm's law, which is that potential difference is equal to current times resistance, and it is a measure of the opposite of flow of current. And then capacitance is a measure of how much charge can be stored on a capacitor per unit of potential difference, and can be calculated doing charge over potential difference, or area times epsilon naught over the distance between the plates. So here is a visual model of the circuit, with the system being the voltmeter or ammeter and the surroundings being the circuit. So part 1, we just created a simple series circuit with 2 1.5 volt batteries, 2 ammeters, one 47 ohm resistor, and one 100 ohm resistor. And the predicted current based off of Ohm's law was 0.0204 amps, and the current measured in the simulation was 0.02 amps. And then when we reversed the ammeter, the current showed as negative 0.02 amps. And in part 2, we got rid of the second ammeter and replaced it with a voltmeter, and it's an open circuit. So the potential difference was 3 volts and the current was 0 amps. For part 3, we measured the potential difference around the circuit. So the values can be seen in that chart, and we can validate that everything follows the loop rule by summing up the different potential differences and seeing that they all add up to 0. And then part 4, we had an ammeter in parallel, and in doing so, we increased the current flowing through the circuit, and the math there shows why that happens. And essentially, because there's no resistance in the ammeter, the flow goes through the ammeter as opposed to the second 100 ohm resistor, and that decreases the total resistance and increases the current. So for part 5, calculating the resistance of the circuit elements, I just used Ohm's law for this, and I was able to calculate the resistance in the 47 ohm resistor to be 48 ohms, and the resistance in the 100 ohm resistor to be 102 ohms, and it's slightly greater just due to imprecision in the simulation ammeter. And then the current flowing through the wire and the ammeter is 0 ohms. Part 6 of this lab, I made 2 RC circuits, one with a 10 ohm resistor bulb and one with a 20 ohm resistor bulb, and I measured the time it took to charge and discharge the capacitors. So for the 10 ohm resistor circuit, it took around 15 seconds, and for the 20 ohm resistor circuit, it took around 30 seconds, which shows that with greater resistance, the greater time it takes to charge or discharge a capacitor. And so then we can also measure time-dependent voltage by having a voltmeter across a charged capacitor, and then removing the battery from the circuit, and then letting the capacitor discharge through a resistor. And so for this part of the lab, I recorded the voltage every second for 20 seconds. And in doing so, I was able to create this graph that related the natural log of the potential difference over the initial potential difference over versus time. And doing that, we were able to get the slope as the negative inverse of RC, or the time constant. And from that, I calculated the time constant to be 6 seconds. In general, the calculated values were greater than the simulated values, and this is due to potential sources of error, such as imprecision of the ammeter, that the simulation is of ideal conditions and lacks real world imperfections, and then also potential rounding errors or timing errors. A real ammeter has non-zero resistance, which means that the total resistance would be larger, and so the current would be smaller. And then wires also have a non-zero resistance, which would also increase the resistance and decrease the current readings. Batteries have an internal resistance, which means that the potential difference across the battery would be smaller, which would decrease the current in the circuit. And as a result, it would take longer to charge or discharge a capacitor.